Exploration with Dr. Michio Kaku, Tuesdays at 4 p.m. Eastern Time on the Progressive Radio Network.
Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. And this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, leading off, we're going to summarize some of the top stories of the past week. Our lead story concerns an announcement made by the astronomical community that is a real game changer. We now realize that there are more planets in the Milky Way galaxy than there are stars. Well, since there are over 100 billion stars in the Milky Way galaxy, that means in our own backyard there are perhaps 160 billion planets, many of them Earth-like. I tell you, this is going to change our whole conception of the night sky and our place in the universe. The fact that planets may actually outnumber stars in the Milky Way galaxy. And then we'll say a few things about consumer electronics. Right now, even as we speak, in Las Vegas, there's the annual Consumer Electronics Store where all the goodies are arrayed for people to gawk at. And there's one device that is generating a lot of excitement. You may eventually find it in your own living room, and that is 3D television without those clunky glasses. Yes, that's right. One of the main reasons why 3D has never really taken off is because you have to wear those dumb glasses in order to get the full effect of things jumping out from the movie screen or the TV screen. Well, now, using physics, we can actually create 3D television without glasses. That's right. In the privacy of your living room, you can get the full effect of seeing movies like Avatar right on the TV screen. And we'll explain why this is possible using physics on Exploration. And then we're going to bring on our special guest today. We're very delighted to have with us David Archer. He's the author of a rather disturbing book called The Long Thaw. Many people realize that with global warming, it means that many of the glaciers on the Earth are receding, the North Pole is getting thinner and thinner, and perhaps the geography of the Earth itself will change as sea levels begin to rise, and this is called the long thaw. And so we're going to take the long view out to 100,000 years. Not just within 100 years, but 100,000 years, humans are changing and accelerating the rate of recession of the glaciers on the planet Earth so rapidly that you can actually make predictions of how humans are going to affect the Earth even perhaps after we're gone. Well, let's just jump right into some of the top stories of the past week. The big story concerns the fact that astronomers have now undergone a sea change in our understanding of the universe. We now believe there are more planets than there are stars in the Milky Way galaxy. So tonight, go outside, look up. I know that's difficult for some people. Most people never look up. However, if you look up at the night sky and you see that there's this whole dazzling array of stars, thousands of stars in the night sky, realize that the latest census of the galaxy shows there could be 60% more planets. 60% more planets than there are stars. So believe it or not, we now know so much about the presence of extrasolar planets that we can actually make a census in the Milky Way galaxy. Well, most of us realize that there are 8 planets in our own solar system going around the sun, Pluto being kicked out of the solar system for being basically an overgrown comet. But there are 8 planets from Mercury out to Neptune in our solar system. However, orbiting other stars that you see at night are other solar systems that can now be confirmed using instruments. Several ways have been devised by astronomers to find the 700 planets that have been confirmed to orbit around other stars. First of all, if a planet the size of Jupiter were to go around our sun, for example, the two would sort of like chase each other like a dog chasing its tail. They sort of like rotate around each other like two dumbbells. So the sun wobbles as a consequence of having a large Jupiter. That's how we determine the presence of a large Jupiter, because Jupiters are dark. They don't emit light of their own, while the stars do. In fact, stars emit billions of times more light than the reflected light coming out from a Jupiter-sized star. So by simply looking at the wobbling of stars and calculating the frequency of the wobble, we can actually prove that there is a planet out there. There's a more direct way with the Kepler satellite that was launched into outer space a few years ago. The Kepler satellite looks for the eclipse of the mother star as a planet goes in front of the face of the star. So there's a slight dimming of starlight from that star, which is periodic as the planet goes around. Now, so far, 700 planets have been found by astronomers using this method. First of all, we find that if you look at the stars in the heavens, most stars are double star systems. They're actually two stars chasing each other, and having a solar system is rather rare for such a double star system. Basically, they would be unstable, though there are exceptions. Most other stars, that is the other half, are single stars, and we now believe that most single stars have solar systems of planets around them. So in other words, roughly 60% of all stars are double stars, and for the most part, they don't have any solar system of planets. But the other 40%, most of them, in fact, have entire solar system of planets going around them. Now, we find that planets come in all shapes, sizes, and temperatures. If you saw the movie Star Wars, for example, scientists have now found planets that look very much like the planets found in Star Wars. For example, Tatooine is the planet where Luke Skywalker grew up, and it turns out that that planetary system is a double star system. Scientists have now found a Tatooine-like planet that goes around a double star system. Though, of course, for most star systems, we have a single star with planets going around them. Now, the holy grail of planetary science is to find Earth-like twins in outer space. Last year, it was announced that we found not one, not two, but three planets that look very similar, but not quite, to the planet Earth. First of all, they are either slightly too big or they're slightly too close to the mother star. If they're too close to the mother star, then a liquid ocean would basically boil off and evaporate. So in such a planetary system, you're not going to find a planet with a liquid ocean. And since liquid water is the universal solvent out of which DNA got off the ground, we think that a liquid ocean is in some sense a necessary prerequisite for finding life in the universe. So last year, 3 planets were discovered that are very close, but not quite the size and the distance from the sun that the Earth is. But this year, many astronomers believe that this year we should find it, the holy grail of planetary astronomy, that is a twin of the Earth in outer space with the right mass, the right distance from the sun to have an atmosphere and to have liquid oceans. And in fact, in 2012, astronomers announced the fact that 3 other planetary systems have been discovered that are actually smaller than the Earth. Now, this is in some sense miraculous. The bigger the planet is, the easier it is to detect. The bigger a Jupiter is, the more wobbling of the mother star. And the larger a Jupiter-sized planet is, the larger the eclipse it makes when it transits in front of the star. Well, Kepler's satellite is so precise that it's been able to locate 3 alien planets that are actually smaller than the Earth. In fact, they are about the size of Mars. And so this is incredible. It means that the Kepler satellite is so sensitive that not only can it pick up about 2,000 planets so far in outer space, it can now pick up planets even smaller than the Earth. So, like I said, we can actually take a census of planets in the Milky Way galaxy. As I said before, for every star, we find that there are 1.6 planets, and for every 20 stars, we find a candidate for an Earth-like twin in outer space. So far, the Kepler satellite has identified 2,000 planets. However, that has to be verified. It has to be verified by ground-based telescopes and sensors. So far, only 700 planets have been confirmed using ground-based instruments. However, the Kepler satellite is paving the way for discovering thousands of planets in outer space. Now, even if we find an Earth-like planet, that doesn't mean we're going to be able to have aliens that phone home like E.T. There are several problems there. First of all, these planets are tens to hundreds of light years away, meaning that even if you were in a Saturn V rocket, it would take tens of thousands to literally millions of years to reach these distant planets. So a two-way conversation is not possible. However, maybe it's possible to eavesdrop on conversations with intelligent life forms in outer space. That's the thrust of the SETI program, the search for extraterrestrial intelligence. However, I should be very careful to point out that so far, after scanning more than 1,000 stars, the SETI project has found not a single candidate for a signal from an intelligent civilization in outer space. Now, that doesn't mean they don't exist. It simply means that so far, scanning only 1,000 stars with any great depth, scientists have been able to find basically nothing, just static coming from distant stars. However, let's be fair about it. There are more than 1,000 stars in the galaxy. In fact, there are 100 billion stars in the galaxy. So we've only scanned a tiny fraction of the stars in the Milky Way galaxy. Not to mention the fact that maybe we're not listening in on the right frequency. After all, we listen in on what are called the hydrogen frequencies because hydrogen is found everywhere in the galaxy. But why should aliens listen in on the hydrogen frequencies? My own point of view is that if you go by an anthill and you see ants busily at work, first of all, do you go down to the ants and say, I bring you trinkets, I bring you beads, I give you nuclear energy, take me to your leader? Or perhaps you have a politically incorrect urge to step on a few of the ants. Therefore, that's probably one of the reasons why they don't want to visit us. We would be ants to them if they can have starships that can visit us from outer space. But second of all, if the ants were to try to listen in on the messages being sent by us, that is, let's say workers are building a 10-lane superhighway next to this anthill, the ants wouldn't have a clue as to what frequencies to listen to. They wouldn't know what to find. They wouldn't know how to go about making contact with the workers. So in other words, there could be intelligent life forms teeming in the galaxy, but we might be listening in on the wrong frequency, looking in the wrong direction, just like ants who are totally oblivious to the fact that intelligent life forms are building a 10-lane superhighway right next to their anthill. Well, let's now say a few things about inner space, specifically consumer electronics. Did you know that the consumer electronics industry is having their gala festival in Las Vegas even as we speak? One device which is attracting a lot of attention is 3D television without glasses. Now, first of all, how do you attain the 3D effect? You do that because, well, we have two eyeballs, a left eye and a right eye. The left eye and the right eye see two slightly different images. The brain puts these two images together, and it gives you the illusion of the third dimension. Now, your brain, of course, cannot see the third dimension because your face is basically flat, two-dimensional, but we have the illusion of the third dimension because we have two eyes. That's the reason why, back in the 1950s, when 3D movies first got off the ground, you had to wear clunky glasses. One glass only let in red light, the other glass let in blue light, and the movie screen had two images, and you filtered out one or the other image and brought them together inside your eyeball. Well, that was pretty clunky. Now we use polarized lenses, and so we don't have red and blue images, but we have full color now in 3D. But you still have to put on those clunky glasses. Well, now there's a new kind of 3D without glasses called lenticular physics. Lenticular physics is when you take two images and you splice them together and you put them in front of a screen with thousands of vertical lines. These vertical lines are in fact prisms, miniature prisms, that bust up the image. One image is sent to the left eye, the other image is sent to the right eye, your brain puts them together, and voila, you have the illusion of three dimensions. These televisions can also lock in on your eyes and know exactly your location, so they would be able to adjust the three dimensions that it produces and lock onto your eyeball, so the sweet spot would be anywhere your eyeball rests. So this is a way to get 3D without glasses. And now I'd like to introduce our special guest for today. He's Professor David Archer, Professor of Geophysical Sciences at the University of Chicago, and he's the author of a rather disturbing new book. And it's called The Long Thaw, How Humans Are Changing the Next 100,000 Years of Earth's Climate. He argues in The Long Thaw that not only are humans ruining the atmosphere of the Earth by dumping copious quantities of carbon dioxide, but the effects of this will linger in the atmosphere, not just for years, not just for centuries, but 100,000 years. And what does it mean? What does it mean for us to live in a world with that much carbon dioxide and that much global warming? So once again, the special guest is Dr. David Archer of the University of Chicago. The book is called The Long Thaw. Professor Archer, as a youth, how did you first get interested in science, and in particular, earth science?
I guess I looked to the Earth, the functioning of the Earth, the stable geochemical cycles of things like that, as something that's bigger than people are. I look to the natural world with a sort of reverence, and I think that's what brought me into the natural sciences. Why I chose to study the oceans actually instead of forests or other planets or stars or something like that is because I've always had a romantic love of boats. But now I ended up living in Chicago anyway. But that's just one of life's jokes, I guess.
Okay, well, let's get right into it. First of all, what is the relationship between carbon dioxide and global warming?
Well, carbon dioxide traps infrared light that tries to leave the atmosphere. It's like if you put a coat on in the wintertime, it traps some of the heat leaving your body, and so it allows your body to warm up. And the theory about CO2, how it affects the climate of the Earth and how much it affects the climate of the Earth, is over 100 years old now. It's very, very solid science. But if there were no greenhouse effect, we wouldn't be able to explain why the Earth isn't in a deep freeze, or the climate of Venus, or lots of other things. It's very solid science.
And, well, talking about Venus, some people call Venus the greenhouse planet. Why would a carbon dioxide atmosphere for Venus make it the greenhouse planet?
Well, there's 70 atmospheres of CO2 in the atmosphere of Venus, so it's very, very thick greenhouse forcing. It has a very strong greenhouse effect. Actually, Venus is also a very reflective planet. That's why it's so bright in the night sky. So if there were no greenhouse effect on either Earth or Mars, even though Venus is closer to the sun, it would be colder than the Earth because it reflects away so much of the sunlight that would heat it up.
Okay, well, now let me play devil's advocate. Some people say, bah, humbug. The current warming of the Earth is a natural cycle. The Earth is naturally warming up. Other people say that it's the sun. Yeah, the sun. The sun is causing the Earth to rise in temperature, not human activity. And other people say that the Earth is cooling. What are your thoughts?
Sometimes it's even the same people who one year say the Earth is not warming up and the next year say that it's warming up, but it's entirely natural. You know, ours is a contentious species. We tend to take both sides of positions, even if there's nothing to base assertions on. If they sound good, they still can carry some weight. The Earth has clearly been getting warmer. That's measured, even though it's been a cool summer here in Chicago. Overall, the average temperature of the Earth is rising. The sun has not been getting brighter. We have good measurements of the intensity of the sun from satellites going back a decade, a few decades. I don't know exactly, but it's not. There's a sunspot cycle that makes the sun brighter and cooler over 11 years, but there isn't a long-term trend at all in the sun getting brighter. So, you know, people say what they, you know, think people want to hear, and people hear what they want to hear, but there is, you know, objective reality. We can measure these things and say what's really going on.
Okay. Well, some of the critics say, okay, so maybe the Earth is getting warmer. However, human activity, some people would say, no, it's not human activity. So what's the reason that many scientists believe that it's human activity causing the current warming?
we can estimate how much warming to expect from rising CO2 concentrations in the air. That's actually boiled down into a number called the climate sensitivity, which is how much the climate would warm if you doubled the CO2 concentration. And the first estimate of the climate sensitivity of the Earth actually goes back to Svante Arrhenius in the year 1896, over 100 years ago, who predicted that doubling CO2 should raise the temperature of the Earth by about 6 degrees centigrade. And now they say it's something like 2.5 to 5 degrees centigrade. It's really not that much of a change. It's a tricky calculation because it's very complex the way that CO2 interacts with light. But this is, by sort of normal non-political rules of science, this is a done question.
So if you, let's say, were to remove humanity from the planet Earth, then you're saying that the Earth would not be so warm as it is today?
There was a model exercise conducted by the Intergovernmental Panel on Climate Change. So these are climate models developed all over the world, and they all subjected their models to one scenario where you tell the models about the rising concentrations of greenhouse gases, and then another scenario where you only have the natural climate forcings like the intensity of the sun or volcanic eruptions can cool down the planet. And if you tell the models about the greenhouse gases, they can explain the warming that has been detected since sort of the 1970s. The temperature since the 1970s, that's the smoking gun for global warming. If you don't tell the models about the greenhouse gases, they don't warm up in the same way. So if you want to say that the warming is real, but it's caused by something that we don't understand in the climate system, which, there will always be things that we don't understand, not only would you like to come up with an explanation of what that something would be in order to settle the question, but you would also have to figure out why the CO2 is not causing the warming that we attribute it to. It's sort of like if you catch, I make an analogy in my classes to a murder mystery, because people always put on their thinking caps when they're reading murder mysteries. They don't always put on thinking caps when they're thinking about science. But so you catch the butler with the gun in his hand and the dead guy, and there's smoke coming out of the gun, and your partner is sort of a contrarian guy. You're a policeman trying to solve the crime. Your partner says, well, I think the chauffeur did it. But for your partner to convict the chauffeur, he's first going to have to explain to the jury what the butler was doing with the smoking gun in his hand. In other words, translating back out of the analogy, if we want to say that the warming is not from CO2, we have to explain what's wrong with greenhouse theory, that the CO2 should not be causing the warming.
Well, if you look at temperature rises over the last many centuries, you see a gradual warming, because after all, there was an ice age 10,000 years ago. But some scientists say that there's a spike that is quite anomalous that is taking place in the last 100 years, and that's proof that it's human activity because it's not part of the natural cycle. What are your thoughts?
Well, there is this large-scale glacial interglacial cycle that you refer to. There's also a sort of a milder, much shorter, I don't know if it's a cycle or just sort of fluctuations, but back sort of between the 1300s and the 1700s was a time of generally cool temperatures called the Little Ice Age. So you could, ice skate in Amsterdam and things like that you no longer can do. And that is correlated with a lack of sunspots, which indicates that the sun was cooler. We don't have satellite solar intensity data going back to the 1600s, but we have observations of a number of sunspots that date back to, Galileo's invention of the telescope in the 1600s, and there's a correlation between the number of sunspots and those sorts of climate changes. I think the evolution of climate up until the 70s, though, can be explained pretty well by natural forcings. It isn't until the 70s that the climate signal the human-forced climate signal started to come up out of the noise of natural variability.
Now, also, some people say that the last decade was perhaps the hottest decade ever recorded. How far back does that go? Because, of course, perhaps during the dinosaur era, things were a lot warmer back then.
Sure. So there are thermometer records that go back to about 1860 from Fahrenheit's invention of the thermometer. They can piece together the temperature of the Earth going back further than that with what they call proxy records of temperature from the widths of tree rings or from chemical measurements they can make in ice cores or sediment cores or something like that. And so they can record, they can figure out that the Little Ice Age was cooler, and then there was a period of general warmth before that called the medieval optimum climate. Those records generally go back 1,000 or 2,000 years, and the conclusion of the last IPCC report, which summarized climate, for non-specialists and for the community outside of your own field, very useful, very, very authoritative reports. They concluded that current temperatures are warmer than they have been in 1,300 years. But if you go back millions of years, you're absolutely right. During peaking about 50 million years ago, the Earth it felt tropical to the poles, and there was no ice anywhere to be found. And this is thought to be due to higher CO2 levels in the atmosphere at that time. We don't have as good ways of estimating what the CO2 concentration was when you go that far back in time, but the evidence that has been pieced together is all consistent, that there's sort of million-year or tens of million-year fluctuations in the natural CO2 levels of the Earth that sort of drifts up and down like that.
Now, scientists that have gone to the poles to extract ice cores, essentially getting ice that was deposited perhaps several 100,000 years ago to maybe 1 million years ago,
yes,
they see that carbon dioxide levels and temperature levels go up and down in unison like two roller coasters. What does that mean?
It's rare that you find such beautiful correlations in nature, I think. It's just astonishing. Al Gore showed this plot in his movie. That's sort of how iconic it is. It's an astonishing thing.
Well, I'm afraid that's it for the first part of Exploration. Once again, you're listening to an interview with Professor David Archer of the University of California, author of a very disturbing new book called The Long Thaw, How Humans Are Changing the Next 100,000 Years of Earth's Climate. And if you want a copy of today's program, call the Pacifica Program Service at 1-800-735-0230. That's 1-800-735-0230 for a copy of today's program. And be sure to dial into my website, www.mkaku.org. Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, welcoming you to the second half of Exploration. In the first half of Exploration, we began a dialogue with Professor David Archer of the University of Chicago, author of a disturbing new book called The Long Thaw, How Humans Are Changing the Next 100,000 Years of Earth's Climate. You know, when we think about global warming, we tend to think of the fact that we will suffer the consequences. We will see the Earth's climate change. We will see the melting of glaciers, the melting of the ice caps, but some people don't think far enough into the future. What Professor Archer is saying is that the amount of carbon dioxide already dumped into the atmosphere will persist for thousands of years, and in fact 100,000 years from now, humans, if we're still around, will bemoan the fact that industrial society, that is, we in our society today, really mess things up. So once again, our special guest today is Professor David Archer. The book is called The Long Thaw, How Humans Are Changing the Next 100,000 Years of Earth's Climate. Now, Professor Archer, when we last left off, we were talking about the fact that ice core data shows that carbon dioxide levels go up and down, but the temperature of the Earth goes up and down, and the two of them go up and down like two synchronized roller coasters. So what does that mean if the ups and downs of carbon dioxide exactly mirror the ups and downs of temperatures on the Earth?
Somehow, the orbit of the Earth around the Sun has these wobbles in it, and that is thought to pace the progress of the ice age cycle, when the ice sheets are going to grow or when they're going to collapse. But somehow the CO2 concentration of the air follows along with the changes in the climate, so that when the orbit tells the ice sheet to make the Earth warmer, the CO2 says, okay, I can pitch in some to that too, and so it amplifies these climate changes.
So which comes first? The temperature rise comes first and then the carbon dioxide rise, vice versa? What's the relationship?
It's a back and forth cause and effect. It's a feedback system. So to ask which one is driving which, I think, is like asking if you see two figure skaters, twirling each other around on the ice, which to try to analyze the trajectory of one without paying attention to the other would make no sense. On the deglaciation, the transition from the ice age climate to the present day climate, the first thing that started to happen, as recorded in the Antarctic ice cores, is a change in temperature in Antarctica. And then a few centuries later, the CO2 concentration started to rise. But then the total change in climate took much longer than a few centuries. So there's no way you could explain the climate transition from the glacial world to the interglacial world without taking into account the change in the CO2 concentration. So it's a feedback loop of cause and effect. It isn't just one or the other drives the thing.
So, summarizing, if you were to go back 10,000 years, we had the Ice Age. Things have been warming up in the last 10,000 years. But is it safe to say that recently, in the last several decades, there's been a spike in temperature rise, and that's due to human activity?
That's more or less true. Actually, the interglacial period is called the Holocene. And the early Holocene, right at about 10,000 to 6,000 or 8,000 years ago, may have been warmer than today. The Earth's orbit around the Sun was in a different, slightly different configuration than it is today. So it almost seemed like there was a peak in warming and then maybe a little bit of gradual decline driven by the Earth's orbit over the millennia. But certainly over the last 1,000 years or two, the temperatures of the last decade are anomalously high.
Okay, let's talk about the present. What's happening with glaciers and the North Pole and the South Pole? We see evidence of the melting of the glaciers around the Earth. That's why scientists are finding so many mammoth bones and even human remains, because the glaciers are receding. So what evidence do we have that the Earth is warming?
Well, we just have the thermometers. I mean, for direct measurements of temperature, thermometers are hard to beat. But the mountain glaciers are almost all melting. It's difficult for a glaciology graduate student to find an advancing mountain glacier to study anymore because there are very few that exist. There's warming detected in the deep ocean, fairly deep, not all the way to the bottom of the ocean, but you can see the warmth sort of penetrating the ocean. In the high latitudes, the Arctic is melting like crazy. It's the sea ice covering the Arctic Ocean is melting much faster than any of the models a few years ago predicted. The year 2007 was a sort of a train wreck for the sea ice up there. It just plummeted. Actually, in the southern hemisphere, it's not so clear what's going on. In the interior of Antarctica, it actually is cooling, which is not. That's something that the climate models also predict. So that's not a discrepancy. But there's also not been a melt back in the sea ice in the Antarctic either. And I gather there's still some messiness about that issue, that maybe it's caused by changes in the circulation of the atmosphere caused by the ozone hole, which is a completely different sort of phenomenon. Ozone is a greenhouse gas, but it also absorbs ultraviolet light, and so it heats up the air that it's in the stratosphere. That's why the stratosphere gets warmer as you go higher up in the stratosphere because of ozone. So by wiping out the ozone in the spring of the Antarctic every year, that changes the dynamics of the air, and maybe that's responsible for a lack of global warming signature generally in the southern hemisphere. Actually, there has been very intense warming on the Antarctic Peninsula, which kind of sticks out from Antarctica up into the slightly lower latitudes. And so you read sometimes in the newspapers about these ice shelves, these very thick floating shelves of ice, hundreds of meters thick. You could walk on it and not know that you weren't on solid land, that suddenly have been collapsing. Places that have been covered by ice for, since the last ice age, suddenly are ice free. So there are signs of the climate change every place. The growing seasons have gotten longer. The Arbor Day Foundation has published maps of climate zones of where you should plant begonias or tulips or whatever, and those have changed since 1990. There are all kinds of signs. It's more obvious in some parts of the world than others. Actually, in Chicago, there hasn't been much climate change since the 70s, but if you go up to Alaska, the climate changes have been huge. So, local experience is not necessarily a good guide, but you put it together into a global average, and it's very clear.
And also, you mentioned how it affects plants and also animals with the changing of the growing season, but also insects, right? Some people are saying that the West Nile virus, which has been spreading through urban centers, is in part driven by global warming, and then in the future, malaria could also spread. What are your thoughts?
I'm not a public health person. I don't really know a lot about the details of this, but people that I talk to are very concerned about the effects of climate on public health. I think the World Health Organization estimated last year that there are 150,000 deaths a year that can be attributed to climate change. Now, obviously, that's a statistical sort of question that's not so easy to answer. But the people that I talk to say that's a very realistic. They have models of disease transmission and everything, and the climate and the insect vectors that carry the diseases are part of those models. Now, that being said, you can do a lot about malaria itself just with, mosquito nets and insecticides and things like that. And so I have heard the argument that instead of paying to reduce CO2 emissions, we should just pay for mosquito nets. I don't think the tropical diseases are the main reason why we want to worry about changing the climate.
Okay, now let's talk about the thrust of your book, which talks about the future, up to 100,000 years into the future. Well, first of all, let's talk about the coming decades. What's happening with the temperature on the Earth? Projections out to 50 years, 100 years. Some people say that on a scale of decades, major metropolitan cities like New Orleans, Boston, New York, San Francisco could be partially underwater. So what are the projections for, let's say, 50 to 100 years?
Well, one of the big uncertainties there is what we do with CO2 emissions and energy, but you can take as a baseline just to talk about what they call a business as usual scenario, which is a projection of how much energy people will need and how much fuel they will burn to get it if there were no constraint from changing climate. And the temperature changes responding to that would put the Earth warmer than it has been in millions of years. So saying what exactly the impacts of that would be on, the corn harvest in Iowa or something like that is really not a very easy thing to do. With respect to sea level, the question is all how quickly can the major ice sheets respond to the changes in climate? The models that have been developed in the past don't respond nearly as strongly as the observations that glaciologists actually can make in Greenland and Antarctica about how the ice streams flowing into the ocean respond to the changes in climate. You can measure more ice quakes in Greenland with seismometers than you could 5 years ago. And the ice sheets, the ice streams flowing from the ice sheets into the ocean are accelerating. So it's really kind of anybody's guess how long it takes for sea level to change. There were events in the past called Heinrich events, when the Laurentide ice sheet, which was in North America, every 8,000 years or so during the last ice age would just collapse into the ocean. And there would be this armada of icebergs in the North Atlantic, and they would carry little rocks and sand and stuff like that would then deposit on the seafloor, and there's no way for those to get there other than these icebergs. And so that's how we know about these events today, is by finding those layers of rocks on the bottom of the Atlantic. Those seemed like they took a century or a few centuries, and they seem, some of them, to have raised sea level by many meters, which is much more than any of the ice sheet models predict for the global warming climate event. But I think a lot of people, most everybody thinks that these ice sheet models are just lacking some essential physics at this point.
Well, some people say that the real problem with sea level rise is simply the thermal expansion of ocean water with the rising temperature of the Earth. And since the Earth is rising in temperature, the oceans are going to expand no matter what happens to the North Pole or the South Pole.
Well, that's absolutely true, and that's part of the forecast for sea level rise by the year 2100, which is about half a meter or so. Something like half of that sea level rise is caused by exactly this effect, the expansion of the seawater. It's like the mercury in the thermometer that fills up more of the thermometer when the temperature goes up. That's a process that will keep going for centuries. So the forecast for the year 2100 is not sort of the end of the line. That's sort of just the beginning for the thermal expansion of seawater. The other half of the sea level rise that's actually in the IPCC forecast for the year 2100 is melting of smaller mountain glaciers like in the Andes and the Alps. And actually a lot of the sea level rise today can be attributed to mountain glaciers in the state of Alaska. It just happens to be a place where there's lots of ice frozen on mountains and where the climate changes are very intense. But it's some astonishingly large fraction of the sea level rise comes from Alaska.
Okay,
just as a curiosity.
Okay, so what does that mean for the average person who has to make decisions, enormous decisions, in the next few years about fossil fuel consumption, about investment in solar energy, and so on and so forth? What changes in their lifestyle should we expect in the coming decades?
Well, lifestyles could change because we adapt to new energy technologies. Most of the CO2 emissions that can be avoided in the next few decades actually come from improvements in efficiency. There are all kinds of factor of 2 and better changes, cuts in energy requirements and CO2 emissions that can be done just by improving the efficiency of how we use energy. The Europeans and the Japanese use half as much energy as the Americans per person, emit half as much CO2, and have a perfectly wonderful lifestyle as far as I can tell. The other way that this issue could impact people's lifestyles could be changes in climate. So you mentioned sea level rise quite a bit. Actually, the issue that concerns me the most on the shorter term is drought. There's already been prolonged drought in the American Southwest and in Australia. And a society can manage a year or two of low water, but if the rainfall, the water availability drops for more than a few years, there's really nothing for it. You can only grow food according to how much water you have. And that could be major adjustments for some people.
some people say that the brunt of this will affect the third world in terms of swings, flooding in some areas, droughts in other areas, rising sea levels, ferocity of storms, insects, devastation of crops. Some people think that the human cost in the short term will be mainly felt in the third world. What are your thoughts?
Well, that was the conclusion of the IPCC. They had a working group that published a big, huge report on the impacts of climate change. And generally, the wealthier the society, the better able it is to insulate itself from climate changes. We can always turn up the air conditioning here in the U.S., and we're not in danger of starving, but subsistence farmers in developing countries live much more close to the land than we do and are more vulnerable. So this raises an issue of fairness. Sometimes people will try to compare the cost of climate change, which they estimate in some way, against the cost of dealing with changing over the energy system, which they estimate in some other way, neither of which are particularly satisfying. But the whole calculation ignores the fact that the people that benefit from business as usual, that is to say us, are not the same people that we're paying the cost of business as usual, which is, I think, as you rightly say, borne more by developing nations. And then the fact that CO2 has such an immensely long lifetime in the atmosphere means that the costs are paid by generations of people way into the future, thousands of years into the future. So, we benefit and they pay. The sort of cost-benefit analysis that you sometimes hear ignores that unfairness.
And your book mentions 100,000 years into the future. Could you elaborate?
When you release new CO2 into the atmosphere, it relatively quickly sort of spreads out through what Earth scientists call the fast carbon cycle of the atmosphere and the oceans and the land surface, the trees and the soils. So right now, the oceans are taking up carbon at a pretty strong rate because the atmospheric concentration, the concentration in the air is going up. But after a few centuries, the CO2 spreads out among those reservoirs, and then it mostly just sort of sits there. On timescales of 100,000 years or something, there's a slow carbon cycle, which involves carbon fluxes to and from the solid Earth. So carbon comes out of the Earth in volcanic gases and hot springs, and it goes back into the Earth when rocks on land dissolve in groundwater, and the rocks are essentially a chemical base, and CO2 is chemically an acid, and so to dissolve the base requires the acid, and it ends up carrying the carbon as limestone into the sediments of the ocean. So that's the pathway for carbon to go back from the fast carbon cycle back into the solid Earth. So this slow carbon cycle is thought to stabilize the climate of the Earth on long time scales. There was an event in the past called the Paleocene-Eocene thermal maximum event. This happened 55 million years ago, and what we know about it mostly comes from sediment cores. Very analogous to fossil fuel and global warming. The CO2 concentration suddenly spiked, and the temperature of the ocean suddenly went up, and then they both recovered on a time scale of 140,000 years for that one. So, that's kind of a model for what would happen to the carbon cycle in the future. The CO2 builds up in all of these reservoirs of the fast carbon cycle, including the atmosphere, and then you have to wait for this slow carbon cycle to slowly clean it up and restore the Earth to its natural trajectory.
Okay, now let's talk about a positive program. President Barack Obama has been talking about a program to rein in global greenhouse gases. People talk about a carbon tax. Some scientists have even advocated technical fixes, some rather harebrained schemes to alter the weather of the entire Earth. First of all, carbon tax. Do you think that's going to work?
Well, the reason why we emit as much carbon as we do is because when you make the decision to, put in an inefficient furnace or an efficient one, or, drive a gas guzzler versus a hybrid, or riding a bicycle or whatever, you're not paying the cost of the climate impacts from that carbon. So economists call that an external cost. So it's external to your decision-making process. Another way of thinking about it is called the tragedy of the commons, where the atmosphere is treated as a common resource, and the costs of exploiting that resource are not paid by the individual who makes the decision, but paid by everybody. And so the natural tendency in a competitive dog-eat-dog world that we live in is for everybody to exploit that common resource to the max, because otherwise, if you don't, somebody else will, and they'll get ahead, and you'll feel like an idiot. And so a carbon tax is a way of, economists would say, internalizing that cost. So you take that into account when you're making your individual decisions. About the schemes to engineer the climate of the Earth, they call this geoengineering. And the one that you're probably thinking about is an idea to put sulfate aerosols or some other little particles up into the stratosphere where they would scatter sunlight back out to space. And it's not really as harebrained as all of that, because big volcanic eruptions do the same thing. Mount Pinatubo was the last one that got stuff all the way up into the stratosphere. If you put particles into the troposphere, the lower part of the atmosphere where all the weather is, they'll just rain out in a week or so. So the stuff that comes out of coal power plants rains out as acid rain, a week or so later, so it doesn't affect the climate of the Earth as much. But if you can put the stuff all the way in the stratosphere, the lifetime of those particles will be several years, because they just have to settle out without the benefit of any rain. And Mount Pinatubo cooled the planet down measurably. Actually, this is a great test for the climate models, because they knew this was going to happen in advance and could, see how the models respond and then see how the real world responded. It cooled the planet down by about a half a degree for a few years. It's not a perfect solution, even in the short term, in that when you trade, so you've got more CO2, and that means you have more infrared light carrying heat to the ground, shining down from the CO2. That's how the greenhouse effect works. And then you compensate for that by putting particles in the stratosphere, so you compensate by sacrificing visible light. And the difference between visible and infrared is that visible is better at causing water to evaporate, because it goes all the way to the ground and then it makes the water evaporate, whereas infrared gets absorbed by the water vapor in the air above the ground. So it warms things up, but it doesn't lead to as much evaporation. So the bottom line is that during those Pinatubo years, the Earth was measurably drier. So if we tried to geoengineer the planet to cool it down, there would be some immediate consequences in terms of drought. But a larger issue about geoengineering is the immense lifetime of the CO2. You can't commit to sending airplanes or rockets or whatever of sulfur into the stratosphere for 100,000 years, because we just don't have that kind of, who can plan that far in advance. And so if at some point in the future civilization, broke down, or for whatever reason couldn't pay their climate bill, they would get the full brunt of all the climate change all at once. I have a colleague here at Chicago who describes the situation as leaving the Earth on life support. Then if there's a power outage, the patient dies. It's just not a good configuration.
Well, one last question. What do you think we should do about this problem?
We should stop building coal-fired power plants immediately. I think that the goal of civilization is to try to protect people from harm inflicted by others. You know, so it's illegal to go and just hit somebody over the head out in the street, even if you want to. And that's a civilizing influence. I think that CO2 emissions are just like hitting somebody on the head. So I think that, properly speaking, it should be illegal to release CO2 to the atmosphere. So, you know, we need to get to that as quickly as we can.
Well, I'm afraid that's it for Exploration. Once again, our special guest was Professor David Archer, author of the controversial new book, The Long Thaw, How Humans Are Changing the Next 100,000 Years of Earth's Climate. And if you want a copy of today's program, call the Pacifica Program Service at 1-800-735-0230. That's 1-800-735-0230 for a copy of today's program. And be sure to dial into my website. It's www.mkaku.org. That's mkaku.org. So once again, this is Michio Kaku for Exploration.